Right, welcome to this video. In this lecture, we are going to talk about logic gates. So if a modern CPU is like a building, then every single logic gate is going to be a brick for that building. So it's super important and fundamental component for any digital circuits in computers, right? So logic gates, first of all, they are physical device. Physical devices. So actually every gate is like a symbol, but finally we do have a circuit in there. It's like a transistor or several transistors to be built in that logic gate. For example, here is one gate, logic gate, have two inputs and one output. You do not really have this kind of shape in a real circuit, but instead of that, what you have over there is the real circuit inside this gate, which are the real physical stuff in a modern CPU, right? Second of all, it has one or more inputs and single output. Okay. There are several, literally 3 basic logic gates. So which means all the other bigger logic gates are so they consist of these basic logic gates. You can use these basic gates to build more complicated logic gates. So they are a NOT gate, AND gate, and OR gate. So these are the 3 fundamental logic gates. And there are several universal gates. So one is called Nand, another one is called NOR. So which means in a real circuit, actually people are using NAND gates or NOR gates trying to build any kinds of logic. So make the circuit design to be simpler or easier. Okay. And also you have arithmetic gates. XOR, XNOR. Right, so we are going to cover all these gates. They are super important. You need to know all of them. But let's start with the basic ones first. Okay. So let's start a new page. One, NOT gate. The symbol for NOT gate is this, a triangle with a little bubble in the front and output. So here's input, here's output, and the logic, if you summarize all the input and possible output in a table, it looks like this. Y is the output, equals to A bar, which is A naught. And if you give a 0, logic 0 to the input, you are going to get a 1. If you give a 1 to the input, you are going to get a 0, right? Very simple logic here. It's just trying to inverse whatever is happening at input. The second one, AND gate. So the way to draw it is like this, a bar here, and then draw arc. 2 input, if we say they are A and B, 2 inputs, and Y as the output. And if you summarize all the possibilities for the inputs in the table, it looks like this. And we can start counting because we have 2 inputs, so the possibilities will be, we can start counting from 0, 0, and then 0, 1, and then 1, 0, and 1, 1, right? So for the AND logic, if you can go back to the video we introduced before, we summarize all the possibilities in the table. If you have a 0 and 0, it's like if you're a coach for a basketball team, you don't have any choice. You have to have both of the 2 players, the bad players on the team, to play the game, right? So it's going to be 0 and 0. Definitely you will lose the game. And same here. So since this is a really bad player, so you have to have this bad player on the team, and then you will lose the game as well. Okay, same here. Only when you have 2 good players, you get a chance to win the game. Okay. That's just the easier method to remember this. Okay, there's no actually players to play any games, right? If you wanna, if you are wondering why we have this example, you can go back to the previous videos when we introduce Boolean algebra and why we get this conclusion here. It's just to try to help you to remember this. And then for the OR logic, when you draw here, starting from here, you are not drawing a bar. Instead, you are drawing a smaller arc and then a bigger arc. Okay, and then 2 inputs A, B, and 1 output Y. So A, B, Y. The same stuff. We start counting from 0 and 1, 2, 3. So totally from 0 to 3, you have 4 possible combinations for the inputs here. So the output will be, since right now it's the OR logic, so the coach has options to pick up which one to be on the team. So you can get rid of the bad players. So 2 bad players, there's no option. So totally lose the game. Here you get a really good player. So why not just pick up this one, do not let this guy on the court. So you will win the game, and win the game. Okay. So these are the 3 fundamental logic gates. And now let's continue with other logic gates. So now here is Nand. So Nand is actually and not. Okay, so you can draw schematic like this. This is and you have an inverter here, right? So if you have A, B, so here what you got here is A and B, and then invert everything here, so you will get A and B not at this point. So that's the final output. However, we have a specific symbol for this kind of logic in this black box to make it simpler. So it's actually just an AND gate and a bubble, right? To make it simple. A, B not. So that is a NAND gate logic, right? So now let's look at the truth table. All right, so the table here is called truth table, right? So we just summarize everything in this table, including all the possible inputs and the corresponding outputs for the inputs. So we have 2 inputs, so we start from 0, 1, 2, 3. Okay, so now let's plug in all these inputs into this Boolean algebra expression, and then let's see what the output should look like here. So 0 and not. So 0 and 0 will be 0 and not. You are going to get 1 here. 0 and 1 is 0 and not. You're going to get 1. Same here. So 1 and 1 is 1, then inverse it, you're going to get a 0. Okay, pretty simple and straightforward so far. And then NOR, it's the same concept. You OR and then not. That's a real logic. or and not, right? So it's actually at this point you are going to get A or B and then invert everything. So why not just do it like this? It's just a symbol, right? Just trying to make it easier for people, like this. So the truth table here will be 0, 0, 0, 1, 1, 0, 1, 1. So or and not. 0 or 0 is 0, not is 1. 0 or 1 is 1, not is 0. 1 or 0 is 1, not is going to be 0. 1 or 1 is 1, not will be 0. So that's a truth table for the NOR gate. And we also have XOR and XNOR. So let's take a look at these ones as well. Then we have all these gates you will see in your life. Not too many, actually. So XNOR. So the XNOR logic, the symbol of that one is when you are drawing a NOR gate, you put a little curly arc in the front, so like this, and then you draw a NOR. So that's the XNOR. And when you draw it, you want this line to cross this arc. So that's A XNOR B. So the XNOR logic is not a, you cannot just build a simple circuit, use transistors in the circuit. So all these XNOR gates are composed of other logic gates like Nand, NOR, because this one we just have a symbol operator here, but actually this one is A not, B not, or AB. So that's a real thing here. So you can see it's composed of an AND logic, OR logic, and NOT logic, right? So let's just label here. So that's an OR, that's an AND, that's also an AND, that's a NOT, right? So that's why we call these gates are basic gates or fundamental gates, actually, because we are using these gates to form other logic here. And now if we have this logic expression, we know actually how to make up a XNOR gates. Right? So just do it in here one by one. So for example, we have A, B as the inputs, and we have A naught and B naught. So that's A and B, right? And here is A naught. Here is B naught. So A naught and B naught, you need an AND logic for these two first, right? So AND logic, that's this part, A naught and B naught, and then you need an A and B. That's A and B. And finally, you need this part or this part. So this is finally A naught, B naught, AB, which is A XNOR B. Right? This is how to do it. So we are actually trying to convert a logic expression to a logic circuit by using these logic gates. You got input, you have an output. To just use a symbol here to replace logic operators in the logic expression, right? Pretty simple. And then XOR, that's the last one I want to introduce, which is you draw this, you draw this, you draw this, but you do not have NOR, but XOR. So you can make it easier to remember is X, when you have an X, is usually referred to this curve here. Okay, NOR is this, right? So X, you need this, OR is this gate. And then you draw two bars, A, B, and it's going to be A, X, or B. So that's a symbol. Here is a circle with a dot in the middle. Here's a circle with a cross in the middle. Okay. And this is actually A not B or A B not. That's a logic expression for this logic. And if you draw the logic circuits for this guy, okay, A, B, A not, B not, right? So A not and B, A not and B, and logic here, A and B not, and logic, and then these two, or logic. So this will be A not B or A B not, which is A X or B. And there are some properties I want to cover for XNOR and XOR, which are a little bit special just for these two cases. So we want to go through this before anything in the homework assignments will possibly confuse you. Okay, so let's summarize all these things here. So for XNOR, XNOR properties, let's get a truth table here first. 0, 0, 0, 1, 1, 0, 1, 1. So for A not, B not, or AB, that's A X nor B. So let's plug in these numbers in here and see what is the result here. Okay, so A not, B not will be 1 and 1, or so 1 or everything is going to be 1. So just put 1 here. This one, A not, B not, you're getting a 0, and AB, you're getting a 0. So it's going to be 0. Same here. For 1 and 1, you're getting A and B will be 1. A naught and B naught will be 0. So you have 1 here. So whatever the other term is, you are going to get a 1. So if you summarize this thing, you will find out for the XNOR logic, so whenever they are different, so whenever A and B are different, you are getting a 0. Whenever they are the same, you are getting a 1. Okay, that's a property for the XNOR logic here. And so when A XNOR A, we already got a conclusion from here. When we have these two terms are the same, when they're the same, we're getting a 1. Right? So when we have these two terms are different, we're getting a 0. And what about this? So by doing this one, you can give examples to A. So if A is 0, 0 X nor 0 will be, because they're the same, so it's going to be 1. If A is 1, 1 X nor 0 will be 0 because they're different. Okay, so if you look at this, the result will be A is 0 is going to be 1, A is 1 is going to be 0. So it's actually A bar will be the result. Depends on what is A, right? So this one equals to A naught. If AX nor 1, so let's plug in the numbers here. So if A is 0, it's going to be 0 X nor 1. They are different, so you're getting 0. If A is 1, 1 X nor 1, they're the same, so you are getting 1. So when A is 0, you got a 0. When A is 1, you got a 1. So the result will be A. For this one, the result is A. So when you are doing this one, you don't know what is A, it's just a case. So in that case, you just want to plug in the numbers to replace A and then trying to find out the result here, right? Now let's take a look at the properties for XOR, then we are done for this video, right? XOR properties. We have A, B, and Y. So for XOR, it's A XOR B. The logic expression is A not B, A B not. So if we have all these possible combinations, the result will be if 0, 0, you're getting 1 and 0, 0 and 1. So finally, the result is going to be 0. And for this one, it's 1 and 1 plus, no plus, or 0 and 0. So it's 1. Yeah, because A and B are symmetric, so 0, 1 or 1, 0 should get the same result. And 1, 1, you're getting 0, 1, so it's 0. Okay, because this is 0, this is 0, 0, 0, 0. That's the final result. And here's a little bit different. We can get a conclusion here, which is a little bit different from the XOR gate. If you look at this, so whenever they are different, you're getting a 1 here for the XOR gate. Okay, that's the difference between this one and XOR gate. Right, so now let's see what are the properties for the XOR logic. Okay, so A, X, or A, so when the two terms are the same, you are actually getting zeros, right? When they are the same, you are getting zeros. When they are different, you are getting 1. And when you have this one XOR with 0, so let's make examples. If A is 0, it's a 0x or 0, you're getting 0. If A is 1, it's 1x or 0, you're getting 1. So when A is 0, you're getting 0. When A is 1, you're getting 1. So actually the result is just A. Okay. So when A XOR 1, it's the same thing. Let's give examples. If A is 1, you are having 1 XOR 1, which is 0, because they're the same. You got 0. If A is 0, you are having 0 XOR 1, you are getting 1. So when A is 1, you are getting 0. When A is 0, you're getting 1. So finally, the result is A bar. Okay. So this is pretty much all the gates you will see in your life for any digital computer systems. And we will just stop here. And in the next video, we're going to introduce XNOR and XOR gates. How can we use these gates as a universal gates? They are super important as well. All right. So thanks for watching, and we'll see you in the next video.